That's great. Okay, so in the last lectures, we talked about the RFM, and we started describing one useful tool for analyzing the RFM called contraction theory. And I gave a very quick lecture about contraction theory. There is a lot to learn about this, but we don't have much time. So today, I want to continue to talk about monotone systems theory. So this is another useful tool for studying many systems, including systems from systems biology, and we will see that it is also highly useful for analyzing the ribosome flow model. So first of all, I want to start with some intuition. And intuition is it's always good to start with linear systems. And let's assume that we actually start with the simplest linear system, which is a scalar system. So I have a scalar linear system, x dot equals ax. And I fix two initial conditions. I fix two initial conditions. Here, I use the initial condition P, some scalar P, and here I use the initial condition Q, some scalar Q, and let's assume that P is smaller or equal to Q. So I have two initial conditions. Since they are scalars, one is smaller or equal to the other. So let's assume P is smaller or equal to Q. Now for this system, of course, we know the solutions. The solutions are just the exponential EAT multiplied by the initial condition. And because P is smaller than Q, we get that the solution, let's denote this like that. XTP is the solution at time t for the initial condition P at time 0, and this is XTQ. And because P is smaller or equal to Q, we see that the solution, EATP, is also smaller or equal to the other solution, EATQ. So in general, what we can say is that the solutions keep the ordering between the initial conditions. There was an ordering between the initial conditions. P was smaller or equal to Q, and we see that the solutions at any time t maintain or preserve this inequality, and this is what we would like. This is exactly the property of monotone systems, and this is what we want to define now for general n-dimensional nonlinear systems. So this is the idea. If the initial conditions are ordered, the solutions are also ordered. Corresponding solutions are also ordered at any time t. So if we want to speak about n-dimensional systems, first of all, we need to order vectors in Rn, because ordering scalars was easy, but now we need to speak about n-dimensional systems, and then we need to order the initial conditions and the solutions, so we have to define an ordering. And the ordering we define is like this. we say that the vector P is smaller or equal to the vector Q if this holds for every entry. So for example, 1, 2, 3 is smaller or equal to this vector because every entry is larger or equal, every entry here is larger or equal than any entry here. So I think that was for n equals 3, of course, but this is well defined and clear, I think, for any order n. You say that the left-hand side vector is smaller or equal to the right-hand side vector if this holds for every two entries that you compare. Now, it is important to note that this is something called partial ordering. For scalars, if I take two scalars, P and Q, two scalars, we always have that P is smaller or equal to Q, or Q is smaller or equal to P. So we can always order scalars with respect to this ordering. But for vectors, it does not work anymore. For example, 1, 2 is not smaller or equal to it is not smaller or equal to 2, 1. Why? This is okay. 1 is smaller or equal to 2, but this is not okay. 2 is not smaller or equal to 1. And also 2, 1 is not smaller or equal to 1, 2. So when I take these two vectors, 1, 2, and 2, 1, I have that this is P and this is Q. P is not smaller or equal to Q, and also Q is not smaller or equal to P. So some vectors cannot be ordered using this ordering between vectors. So that's why it is called partial ordering and not an ordering. Okay, once we define this partial ordering, we can define, this is definition 4 in the lecture notes that I'll send you, we can define what is a monotone dynamical system. So the system x dot equals fx. Now we have an n-dimensional nonlinear system, a general system, is called monotone. If whenever I take two ordered vectors, P smaller or equal to Q, I take two ordered vectors, then the corresponding solutions I take two ordered initial conditions, any two vectors P and Q, which are ordered according to smaller or equal than 2. And when I look at the solutions, this is the solution emanating from P at time 0, and I look at it at time t. And this is emanating from Q at time 0, and I look at it at time t. And when I compare these solutions, they are also ordered for any t larger or equal to 0. So this is exactly what we saw when we consider the scalar linear system. Now we want it to hold for general nonlinear n-dimensional systems, and if it holds, then we say that the system is monotone. It preserves the ordering between the initial conditions. At any time t, when you look and compare the solutions, they are also ordered. So if I try to explain it using a scalar picture, just for the explanation, everything we speak about now here is n-dimensional, but just for the explanation, the idea is like this. I start from two initial conditions, P smaller or equal to Q, and I look at the solutions emanating from these initial conditions. So I don't know, this is XTQ. And XTP should always be below, this says that XTP is always below XTQ. So you can look like this, perhaps, but they can never switch their ordering. XTQ will always be above XTP. That's what this says. Once I heard a lecturer explaining capitalism in this way, in theory, you can imagine a rich person and a poor person. In theory, the rich can become poorer and the poor can become richer. But in practice, whenever they try to switch roles, somehow the dynamics pushes them back so that the rich becomes richer again and the poor becomes poorer. So I don't know if that's a very optimistic explanation, but anyway, I think this explains the basic idea. So questions about the definition of a monotone systems, a monotone dynamical system. Any questions? If something is not clear, that's a good point to ask. If you cannot see me well or hear me well, it's a good time to tell me because I can hopefully still fix it. Okay, so I continue, but please, if there is any problem or anything unclear, or if you have any questions, just barge in and ask, don't hesitate. You can see all the board? Yes?
Yes, sir, the board is visible.
Oh, good, excellent. Let me just copy here what is a monotone dynamical system. Since I raised it, I just wanted to keep the definition here. So if I have two ordered initial conditions, the solutions are also ordered for any time t. So let's put this, now what do we want to do? In the last lecture, I defined what is a contractive system. And then I did two things. I described a condition guaranteeing that the system is contraction, using matrix measures. And I spoke about the implications of contractivity. What does it mean if a system is contractive? So today I want to do the same plan. I want, first of all, to give a condition guaranteeing that the system is monotone, guaranteeing that this holds, of course, without computing the solutions, because in a nonlinear system, unfortunately, we never know the explicit solutions, or almost never know. So how can we deduce that the system is indeed monotone without solving the equations, or without knowing this and this explicitly? That's the first question. And the second question is, okay, now we know that the system is monotone. For example, we will show that the RFM is a monotone dynamical system. What does this imply? What are the implications of monotonicity? So the plan is how to prove monotonicity. And two, what does monotonicity of a system, what does it imply? These are the two questions that we would like to address. Okay, so to address topic number one, we introduce a definition. A matrix We take a n by n matrix, a square matrix with real entries, and we say that the matrix is Metzler. This is named after a scholar who worked in economics. It's called Metzler if Aij is non-negative for every I different from j. So the off-diagonal entries, these are the off-diagonal entries of the matrix. They should be non-negative. So if I look at A, suppose that A is 3 by 3, as an example, I look at A just as an example, which is 3 by 3, then I ignore the diagonal entries because I'm only interested in entries I different from j. And all these entries, the off-diagonal entries, they must all be, the off-diagonal entries must all be non-negative. Then I say that the matrix is Metzler. And the linear system x dot equals ax with A Metzler, so A has this structure, is called a cooperative linear system. I want to explain first of all why is it called cooperative, and then we will relate it to monotone system, to monotone system theory. Let's look at the system x dot equals ax. And again, for simplicity, let's assume that A is 3 by 3. A is Metzler. I want to explain why this system is called cooperative. So I look at this system with A Metzler, and let's consider one of the state variables. X3 dot, because it's a linear system, the equation for X3 dot is what is written here. Now this I don't care about because I impose no condition on the diagonal terms, ignore this. But this, by definition, is non-negative, and this, by definition, is non-negative. So what does this mean? This means that if I increase x1, x3 dot will increase, right? If I increase x1, this is multiplied by a non-negative term, so this can only increase x3 dot. And if I increase x2, then this can only increase x dot. So in this respect, the state variables cooperate with one another. X1 and X2 cooperate with X3 in the sense that when X1 and X2 increase, so will X3 dot. And the same cooperation is satisfied between any two state variables because of this Metzler property. So that's the reason for the terminology cooperative. The state variables cooperate with one another. Now, the proposition relating this monotonicity and cooperativity. This is proposition 6 in the lecture notes that I will send you. The linear system a linear system x dot equals ax is monotone, so it satisfies this property if and only if it is cooperative. So if and only if A is a Metzler matrix. So for linear systems, we have a very simple condition for monotonicity, a very simple condition for this. We just look at the sign pattern of A. We look at the signs of the entries of A, and the off-diagonal entries must be non-negative. And I will try to prove this because the proof is not complicated, and I think it gives some intuition on why cooperativity and monotonicity are equivalent. So let me try to give a proof, just to explain why this works. So we have to prove that we need to show that the system is cooperative, that is, A is Metzler, if and only if the dynamics is monotone. So assume, first of all, that A is not Metzler. And later on today, we will see how all this relates to the RFM. The RFM is a monotone dynamical system, okay? We will get there. But I'm teaching this general tool because I think it is interesting and useful also for many other models in systems biology and in other fields. So first of all, assume A is not Metzler. What does this mean? Then there is some off-diagonal entry which is negative, because Metzler means that all the off-diagonal entries are non-negative. If it is not Metzler, then there is at least one off-diagonal entry, Aij with I different from J, which is strictly negative. Fix an initial condition x0 like this. It is 0 everywhere except for one in entry J of x0, of the vector. Fix such an initial condition. And then let's see what happens. Let's see what happens. What is the derivative in my dynamical system? This is my dynamical system. What is the derivative at time 0? So by definition, x dot at time 0 is ax0. So this is A multiplied by this. And I will be interested in what I see in entry I of x dot 0. I'm looking at x dot 0 and I'm interested in the entry number I. So what do I see in entry number I? This is AI1, AIJ, AIN multiplied by x0. And then I see that I get here Aij, which is negative. So the conclusion is that xi dot at 0 is negative because I get Aij, and Aij is this entry in the not Metzler matrix, which is negative. Now, xi times epsilon xi times epsilon is epsilon small is xi times 0 plus epsilon xi dot 0, which is 0 plus epsilon aij. Here epsilon is positive and small, and this is negative. So I get that if the matrix is not Metzler, I have this vector as an initial condition, and then for small epsilon, entry I of the solution at time epsilon will be negative. Now let's try to see what this means. Let's try to see what this means. We have, let's compare two initial conditions. One initial condition is this one, which I denote by EJ. This is the jth column of the identity matrix. So let's denote it by EJ. And of course, and this is the zero initial condition. And of course, this is larger or equal, this vector EJ is larger or equal to the zero vector because every entry in EJ is larger or equal to zero. And now let's look at the solutions. If the system was monotone, then I expect to see this for every t. Had the system been monotone, we would expect to see this. Now, what is xt0? When I start in my linear system at 0, I stay at 0. So this is just 0. Yes, my linear system, for the initial condition 0, I stay at 0. So had the system been monotone, I would expect to see this, but I don't see this. Why? Because here I have a negative entry. So a negative entry is not larger or equal to 0. So the conclusion is that I found two ordered initial conditions, but the solutions do not satisfy the condition for monotonicity. In particular, at the time t equal to epsilon, with epsilon small, we lose monotonicity. So, not Metzler, what did we prove? We proved that not Metzler, not Metzler, x dot equals ax, not monotone. This is what we proved so far. Questions about this? Please don't hesitate if something is not clear. This is half of the proof. We need to prove that the system is cooperative, that is, that A is Metzler, if and only if it is monotone. We just showed that if it is not Metzler, then it is not monotone. Questions?
Excuse me, sir.
Yes, please.
Sir, please explain the last part again.
Can I explain the last part again?
Yes, sir. The last one.
Here?
Above this. From above this. Yes, sir. Yes, yes.
From here?
Yes, sir. From this till last. The last side of the yes, sir. Yes.
Okay, from here. Very good. So I took as an initial condition this vector that I called EJ. This is the vector with all zeros except for one at entry number j. At entry number j, I plugged in a 1. All the other entries are 0. And I want to see what is the derivative at time 0. Yes, I have my dynamical system, x dot t equals to axt. And in particular, at time 0, this is the dynamics. Time 0, the dynamics is x dot at 0 is equal to ax0, because this is the differential equation at any time, also at 0. Now, let's see what is x dot at 0. But actually, it will be enough for me to look only at the ice entry of x dot at 0. So I just look at entry number I. What is entry number I? X dot at 0 is ax0, so I take my matrix and I multiply it by x0. X dot at 0 is ax0, so I multiply a by x at 0, and I only look at row number I. What do I get at row number I? I get the ith row of A. This is the ith row of A, multiplied by EJ. Now, because EJ has only one entry, which is non-zero, all the other entries are 0, it will just give me, when I multiply the ith row of A by EJ, it will just give me Aij, that's all. Because I multiply this by 0, only this entry is multiplied by 1, and I get this. And this is negative, because we assume that the matrix is not Metzler. There was at least one off-diagonal entry, which is negative. Okay, so I know now that the derivative of xi at time 0, the ith entry of x at time 0, the derivative is negative. Now, let's calculate what will be the value of xi at time epsilon, with epsilon positive and small. It is xi 0 plus epsilon xi dot 0 plus terms that go like epsilon squared and epsilon to the power of 3. But if epsilon is very small, then this will determine the sign of xi epsilon. Now, xi at time 0 is this vector, and when I look at entry I is different from j. I see a 0 there, because the vector only had one at entry j. Now I'm looking at entry I with I different from j. So I have this, which is 0, and this, as we already saw, was just aij. So this is positive, this is negative, so this is strictly negative. And the terms with epsilon squared, epsilon to the power of 3, and so on, if epsilon is sufficiently small, the sign will remain negative. So we prove that xi at epsilon for some epsilon sufficiently small will be negative. Now let me show that this implies that the system is not monotone. We take two initial conditions, the 0 vector and Ej. Ej is larger or equal from 0. So we take two ordered initial conditions. If the system is monotone, we will have this property at any time t. xt0, the solution corresponding to this, and xtej, the solution starting from here, should be ordered because the initial conditions are ordered. And if the system is monotone, it preserves this initial ordering. But this is 0, because for a linear system, if you start at 0, for this system, 0 is an equilibrium. So if you start at 0, it stays at 0. And this is the solution here, but we saw that this has one entry which is negative. So here I have a negative entry. Here all the entries are 0, so it is not ordered anymore. Once we have here zeros, and here we have a negative, strictly negative entry, this is not ordered. So because it is not ordered, I found two ordered initial conditions, and I found that the solutions do not satisfy, they do not satisfy this for every time t, because there is some time epsilon where this does not work. So the conclusion is, thank you for asking, the conclusion is that the system cannot be monotone. So if A not Metzler, x dot is not monotone. This is half of the proof. Now the second part of the proof is to assume A is Metzler. Assume that A is Metzler. Then all the off-diagonal entries are non-negative. So what does this mean? all these entries are non-negative, and these entries, they can be positive or negative or zero, I don't know. These entries, I don't know. Let us define by S the minimum of all the AIs, and then take absolute value. So some of these entries may be negative. I take the most negative entry, because I take the minimum. I take the smallest entry or the most negative entry, and then S is just the absolute value of this most negative entry. So if, for example, if A is like this is a Metzger matrix, then S will be just 5. Okay, maybe 5 is confusing because of the S. Let's take 4. We take the minimum on all the diagonal entries, which can be negative or positive or 0. And then I take the absolute value, and this is S. So in this case, S will be 4. And then I define a new matrix. I take A, and I add S multiplied by the identity matrix. Now, what can I say about this matrix? All entries of B are non-negative. I claim that now all the entries of B are non-negative. Why? The off-diagonal entries of B are just the off-diagonal entries of A, and they are non-negative because I assume that A is Metzger. I assume that A is Metzger. The off-diagonal entries are okay. And what about the diagonal entries? Well, now that I added this S, I claim that all the diagonal entries are also non-negative. For example, look at this example. This was A, this was S. What is B here? This is -4, 2 minus 3, plus 4, 1, 1. This will be the matrix B in this case. You see, the 4 on the diagonal will make this 0, and will make this 1. Because I took S as the minimum of all the AIs, and then with absolute value, then I shift all the diagonal entries and make them non-negative anymore. And the off-diagonal entries were okay already because A is Metzger. Okay, so B is all its entries non-negative. Now look at EBT, the transition matrix corresponding to B. This is I plus B squared. The transition matrix corresponding to EBT. Now because B is non-negative, B squared will be non-negative entry-wise. Now when I say non-negative, I mean entry-wise non-negative. So everything here will be entry-wise non-negative for any t larger or equal to 0. I multiply this b and b squared and b to the power of 3. But since all the entries of b are non-negative, all the entries of b squared are also non-negative, and all the entries of b to the power of 3 are also non-negative. So for any non-negative t, all the entries of EBT will be non-negative. Very good. Now we can almost complete the argument. So let me just summarize what we did here. We define B as A plus SIN for some S, and then this B is non-negative, and then EBT, this component is non-negative for every T. This I erase. Now we prove monotonicity. So what do? We fix two initial conditions, P smaller or equal to Q. And we look at the corresponding solutions. Okay, we look at this corresponding solution. First of all, let's look at EBTP and EBTQ. Okay, and fix also some non-negative time t. First of all, I claim that EBT P, this is a vector, it will always be smaller or equal to EBTQ. Why? Because every entry in B is non-negative. So I take my matrix with non-negative entries and I multiply by one vector, and here I multiply by another vector, but the vectors are ordered, all the entries are ordered. So when you multiply them by a matrix with non-negative entries, this will also be ordered. I hope this is clear. You can write it down and check. This follows immediately from the fact that P is smaller or equal to Q, and that every entry here is non-negative. This is just the product of non-negative numbers, and in the product of non-negative numbers, if you take one number or one vector smaller than the other, when you multiply by non-negative numbers, this will be conserved. This property will be conserved. Now, what is this? This is SIN plus A TP ESIN plus A Q. This is simply because B was defined as A plus SIN. And this, I know what this is. I know because IN and A commute, IN, the matrix, the identity matrix, and the matrix A commute for any A. I know that this matrix exponential is just what I wrote here. Now, this is just a non-negative scalar. For any T, this is just a non-negative scalar, and I can remove it from this inequality without changing nothing. I do not change the sign when I cancel out a non-negative constant in both sides. So I conclude that for an arbitrary T, if the initial conditions satisfy this, then I also have that the solutions satisfy this. Yes, this is just a solution XTP and XTQ of my linear system. So the conclusion was that if the initial conditions are ordered, the solutions are ordered at time t, and time t was a completely arbitrary non-negative time, so we proved monotonicity. So if A is Metzler, we showed that x dot equals Ax is monotone. And this completes the proof that said that we have monotonicity if and only if A is Metzler, that is, if and only if the linear system is cooperative. Questions about this? Here is a good place to stop for questions. So the idea was just to show you why cooperativity and monotonicity, at least for linear systems, is equivalent. Okay, there are no questions. If there are no questions, let me just say a remark. There is something called positive systems. What are these positive systems? Let's think about positive linear systems. So you have a system like this. Now, in a positive system, the idea is that the state variables represent some quantities, some physical quantities that can never be negative. Let's write like this. Does not make sense. For example, imagine that the state variables represent concentrations of molecules. So if they represent concentrations of molecules, the concentration can never be negative. Or imagine that the state variables are densities of ribosomes, like in the RFM. Densities of ribosomes can never be negative. Or imagine that the xi's are probabilities. Probabilities can never be negative. So when the state variables, by their physical meaning, cannot be negative, what do we need? What do we expect? We expect that any initial condition is larger or equal to 0, because we start from feasible initial conditions. The initial conditions cannot include a negative entry. So this is exactly what's written here. Every entry of x0 is larger or equal to 0. This is the legitimate class of initial conditions, because this does not make sense. And then we expect, what do we expect? We expect that the solution will also always be non-negative component-wise, because again, the state variables, it doesn't make sense if they are negative. So this is what we expect. And this is exactly monotonicity. Why is this monotonicity? Because this is the solution corresponding to 0. I can write here x is 0. For a linear system, this is just a solution corresponding to 0. And here I can write the solution from x0. So the condition that the state variables will remain non-negative for any time t, because otherwise it doesn't make sense. This is exactly the condition that if we start with such an initial condition, this is just 0, yes? Or if we have monotonicity, then we have immediately, or this is equivalent to this property of keeping all the state variables non-negative if we started from such an initial condition. And again, if one of the state variables suddenly becomes negative, it doesn't make sense, because we are modeling physical quantities that have to be positive. So positive linear systems are just monotone systems, and by what we just show, all we need is for A to be met. This is a necessary and sufficient condition in order to guarantee that the system is positive. Okay, now I will give a proposition. Okay, first of all, a definition. Now we consider, up to now, we spoke about linear systems. Now let's speak about cooperative systems, about nonlinear systems, sorry. The nonlinear system, x dot equals fx, is called cooperative if dfi dxj we erase this. This is a definition. Now we want to define what is a cooperative, what is cooperativity for a nonlinear dynamical system. So what will I do? I will look at Fi, the ith entry of F, differentiate it with respect to xj, but only for I different from j, and I want this to be always non-negative. Now remember, what is this? This is just xi dot, yes? Sorry. This is just this. Fi is just xi dot. So again, it is the same meaning. When I increase xj, I can only increase xi dot for every I different from j. That's why the state variables cooperate with one another, and the system is cooperative. Now, a main theorem that I will not prove if x dot equals fx is cooperative, then it is monotone. So this is exactly the same situation that we had in linear systems. Well, in linear systems, this was if and only if. For our purposes and for nonlinear systems, it is enough to know that if the system is cooperative, then the flow reserves the ordering, so the system is monotone. And after what we saw for linear systems, I hope that it's not surprising to see this result. I will not prove it, it's in the pages, but just state it. We proved it for linear systems. For linear systems, we proved even something stronger, that monotonicity is completely equivalent to cooperativity. You'll believe me, and it will be in the pages I sent you in the lecture notes, that this theorem holds for nonlinear systems. And what does this mean? Remember that we defined the Jacobian this Jacobian, which was to differentiate every entry of f with respect to a state variable. So this condition, cooperativity, just means that J is Metzler for any x. And then if we have that Jx is Metzler for any x, then this will imply, by this theorem, monotonicity. Cooperativity, by definition, is just to look at these entries, off-diagonal entries of J. These correspond to off-diagonal entries in J, and see that they are non-positive. But this is just the Metzler property. And by this theorem that I stated, this implies monotonicity. So to conclude, let us just show that the RFM is cooperative, is a nonlinear cooperative system, and therefore it is a monotone system. So I will do this for the two-dimensional RFM. Just for simplicity, everything I say holds for any dimension. Just for simplicity, I will now talk about the two-dimensional RFM, just for simplicity. So I calculate the Jacobian. And all I have to do is to check that the Jacobian is Metzler. So because of that, I don't even calculate the diagonal entries, because the Metzler property only requires to look at the off-diagonal entries. So I ignore the diagonal entries altogether. And I calculate here, I need to differentiate this with respect to x2. This is what I get here. And I need to differentiate this with respect to x1. This is what I get here. Now, this is always non-negative because lambda 1 is positive and x1 is between 0 and 1. And this is always non-negative because lambda 1 is positive and x2 is always between 0 and 1. So this term in the brackets is between 0 and 1. So the conclusion is that Jx is always Metzler. So the RFM is cooperative. So the RFM is monotone. I did this for the two-dimensional RFM, but this actually holds for any dimension n. You can easily check this. So I think that's enough for this first lecture today. We are close to 10. And just let me see, it was from 9 to 10 my time, right? So I'm not confused again. Yes, from 9 to 10. Okay, good. So I will stop here, and we will now, in the next talks, we will talk a little more about what does it imply when a system is monotone. We already know how to check and verify that the system is monotone using cooperativity. And we will try to explain what does it mean that the RFM is monotone. What does it mean intuitively? This will be in the next lecture, which is at 11:30 my time. So I think it is 1 o'clock.
Yes.
2 o'clock.
2 o'clock. 2 o'clock.
2 o'clock. Sorry.
Just 1 o'clock.
2 o'clock. Yes. So 2 o'clock your time. Okay. Any questions before we conclude this lecture today?
Hi, Michael. Good morning.
Good morning, Aditi.
Yeah, Michael, we have a definition for time invariant systems of monotone dynamical systems. Is there any variation for monotone dynamical system for time varying systems? Any definitions on that or any theory that has been developed to understand?
That's a good question. The answer in general is that there is a theory of monotone dynamical systems for much more general systems than I speak here. There is a book by A. Smith on cooperative systems, and there he speaks about flows, much more general flows than I describe here. For example, these flows can correspond to the solution of a dynamical system with a time delay.
Okay.
And of course, this can also represent perhaps systems with time varying vector fields, but this requires much more work. So I only considered the case of time invariant systems here. But the definitions and the results, many of the results hold actually for more general systems, and you can find them in this book.
Oh, okay. Okay, thank you.
Thank you, Aditi. Okay. So, more questions?
I think there's no other question. So let's stop this session. We'll see you at 2 o'clock.
I'm sorry, but can you quote the microphone because I can't hear you?
Yes? Michael, come again? Michael.
Yes, more or less. Yes, please.
Will. So what did you say, Michael? Can you come again?
Sorry, can you ask again, please?
So just I was telling like we can meet at 2 o'clock.
I'm sorry, I can't hear.